Hello everyone, my name is Vaibhav Rane, and in today's presentation we are going to talk about the element distinctness problem. So this presentation is for the course COT 5405 under Dr. Sharma Thankachan. So let me give you the outline of this presentation. So first we'll talk about the problem statement and discuss what exactly the element distinctness problem is. Secondly, we'll discuss some of the approaches to solve this problem and we'll analyze each of the approaches we'll discuss. And third, in the end, we'll be proving the lower bound proof for this problem. So let's have a look at the problem statement. So the problem asks if all the n elements in the given array are distinct or not. So for example, in the first array, we can see that 6 is repeated. So the output is going to be no. And in case of second array, we can see all the elements are distinct. So the output of this algorithm is going to be yes. So the output is going to be either yes or no. Now the model of computation for this problem is comparisons. That is, the problem is based on comparison-based model, which allows you to compare two items at a time. So now with this background, we can go ahead and discuss the possible solutions to solve this problem. So the first solution that we are going to discuss is by sorting. So with this approach, what you can do is first we can sort all the elements of the input instance using one of the efficient sorting algorithms in n log n steps. We can use algorithms like merge sort for this. Once these elements are sorted, sorting helps to bring the duplicates element right next to each other. So once the sorting is done, all we have to do is we have to compare all adjacent pairs. So now this comparison operation is going to take n minus 1 steps, and the complete algorithm can be completed in n log n plus n minus 1, that is big O of n log n steps. The second approach that we are going to discuss is hashing based. So we can use hashing to map every element of the input to the corresponding location in hash bucket. So basically the function of hash function is to calculate a certain value which maps your input to a location in hash buckets. So hashing is used in some of the data structures that maintains uniqueness of data, like hash map, hash table, or hash set, etc. So we can use this feature of hashing in order to estimate the distinctness. Now the problem with hashing is that the performance depends on the hash function, how efficiently the hash function hashes the input. So in worst case, what could happen is that for every element in an array, the hash function could return the same bucket number. So this case is called as collision. So collision is that where all the elements are mapped to the same location. That's when we call it as a collision. So there are many ways of handling collision. One of the ways is by open chaining. So with this, what we do is we maintain a linked list of overflow buckets where we keep the collided input items like this. Now in this case, what happened is for every element will be performing hash, will calculating the hash, and after calculating hash, we'll be traversing this list. So it is going to be big O of n squared in worst case. Now let's talk about the decision tree model. So decision tree model is basically a way of modeling the possible execution flows that an algorithm could follow and is represented as a tree structure. So every node that is not a leaf node represents input items. So edges represent operations to be performed on the input items. And finally, the leaf node represent the end states of the algorithm. So in our case, if we uh, try to model the element distinctness problem as a decision tree, our leaf nodes are going to represent either yes or no. So let's take an example to understand how we can model a problem using decision tree. So here's an example of a decision tree for sorting algorithm. So as you can see, every node except for leaf nodes are labeled as I, j. So for example, in leaf node, we are comparing first and second elements. Also, you can notice that all the edges are marked with relational operators. So what does that mean? Is that if in order to reach this node, you need to make sure that your first element is less than or equal to the second element. That's the only way you could reach this node, right? So if you follow this flow, ultimately you'll reach the leaf node that gives you your final decision. So let's consider this example of an array with size 3. So when we reach here at the root node where the algorithm begins, it says that we are comparing first and second element. So first and second element is 3 and 12. So 3 is less than or equal to 12. So we'll follow the left subtree. We'll follow this branch and we'll reach here. So on reaching here, what we are doing is we are comparing second and third element, which is 12 and 4. Now 12 is definitely greater than 4, so we'll take this right subtree branch and we'll reach this node. Here we are comparing the first and third element, that is 3 and 4. So 3 is less than or equal to 4. So we'll take this branch and we'll finally arrive here. So this is the leaf node. So what does leaf node tells us? It gives us the final sequence in which the array should be sorted. So 1, 3, 2, what does it mean? The first element should be 3, the second element should be the third one, which is 4, and the third element should be the second element, which is 12. So it gives us the sorted sequence. So now let's have a look at how we are going to prove the lower bound for element distinctness problem. So we are going to prove this in 3 steps. We'll be providing 3 claims and we'll prove each of them one after another. So the first claim states that if R of L is a set of instances for which the execution reaches the leaf nodes of the decision tree, then R of L is convex region. Claim 2 states that if X is a set of n distinct instances and Y is a set of, again, n distinct instances where Y is a permutation of X, then X and Y must reach distinct leaf nodes. And third, finally, we are going to prove that it takes at least n log steps to solve the element distinctness problem. So we'll be discussing all these claims in details in the upcoming slides. So let's have a look at the claim 1 that states that if R of L is a set of instances of size n for which the execution reaches the leaf nodes of the decision tree, then R of L is a convex region. Okay. So before moving ahead with the proof of this claim, let's first understand certain terminologies used in this claim. So we are trying to prove that R of L is a convex region. Okay. So what exactly is a convex region? So convex region is a region where if a straight line is drawn joining 2 points within that region, that line should completely lie within that region, within the same region. So if you look at these 3 examples here, the first 2 examples, they are definitely not convex regions because as you can see the line joining x1 and x2 it doesn't completely lie within that region. In case of third example, it is clearly a convex region. Also, in this claim, we are saying that RL is a set of instances of size n. So, for the sake of this proof, we are assuming that an instance of n size is assumed to represent a point in n-dimensional space. We'll discuss this in more detail in next slides. Also, why we are representing an instance as a point in n-dimensional space, because representing an instance as a point in n dimensions gives us an important insight that is going to be helpful to prove this claim. So let's take an example. Let's say an instance is of size 2. So if n is equal to 2, it can be represented as a point in two-dimensional space. So as you can see here, in the two-dimensional spaces where dimensions are x1 and x2, the points can be represented as follows. So it can be represented as a unit square. Now, as you can see, this diagonal highlighted in red, for all the points that lie on this diagonal, x1 is going to be equal to x2. Now, for all these points, decision is going to be no, as x1 is equal to x2. That means they are not distinct. Okay. For the rest of the points, for the rest of the region that lie on either side of this diagonal, the answer is going to be, the decision is going to be yes, as x1 is not equal to x2 for both of these regions. So it gives us an important insight that is going to be helpful to prove this claim. So now let's come back to our claim. Now, since let's understand how many instances are going to visit the root node. So all the instances would visit the root node as it is the starting point of the algorithm. Okay. Now, let's see how many elements, how many instances are going to reach this n1 node. So only those instances would visit node n1 whose ith coordinate is smaller than the jth coordinate. Okay. So what we can say from this flow is that on every node visit, we are slicing down the instance space. Number of instances at root node were definitely more than the number of instances at n and n1. Okay, so that's an observation that we should keep in our mind. So we can discuss this in more detail with 3 dimensions. So let's consider an instance with n is equal to 3, that is, the length of instance is 3. So it can be represented as a point in 3-dimensional space, right? So all the instances with n is equal to 3 can be represented as a unit cube in 3 dimensions. So you can say that all these instances would arrive at root node, right? Now let's say in order to reach here, what's the condition? x3 has to be less than x1, right? So when we travel from root node to n1, what's going to happen is some of the instances would be filtered out. So if we see here in the next figure, the area that is highlighted with red is the only set of instances that is going to reach n1. As for this area, all the points are going to satisfy this condition, x3 is less than x1. So this area will get further divided as it travels down the tree. Okay, so now let's come back to the proof again, finally. So let's assume that there are 2 points, x with size n with n elements, and y with the same size, and they both belong to R of L, which means that for execution with x as input, leaf node L is going to be reached, Also for execution with y as input, we are going to reach the leaf node L. Now let's assume that there is a point z with length n where zi is equal to lambda times xi and 1 plus 1 minus lambda times yi for all I. And the value of lambda varies between 0 and 1. So by doing this, we are ensuring that z will be on the straight line segment joining x and y. Now in order to prove that R of L is convex, we need to prove that the straight line path lies within R of L. Okay. Now let's assume that root node is labeled as I colon j, that is we are comparing ith and jth element here. And let's say a less than branch is taken in execution 1 with input x. So when we are trying to execute with input x, let's say we reach here. Okay. Now for execution 2 with y, we can also say that y will also take the same path. Y will also reach the root n1 here. Why? Because they both lie in the region of L. They both will reach the leaf node. That means y must follow the same path as that of x. So we can say that y also reaches n1. It also takes the less than branch. So from these 2 points, what we can say is x of I is less than x of j and y of I is less than y of j. Now, what we'll do is we'll multiply the equation 3, the inequality 3 with lambda, and we'll multiply inequality 4 with 1 minus lambda, and we'll add them. So the resultant inequality is going to be this. Now we observe closely, the left part is nothing but zi as per the definition of z, and the right part is zj. So this inequality becomes zi less than zj. So what we can say from this is that the point z also took, the instance z also took the same path. It also took the less than branch, just like x and y. So from this we can say that z will follow the same path as that of x and y and will ultimately reach the leaf node L. So for any point on line segment will reach L. Therefore we can safely say that R of L is a convex region. Okay. Now let's come to the claim number 2, where we are saying that there is an instance X with n distinct elements, and there is an instance Y, again with the n distinct element, but Y is a permutation of X. So in this case, we are claiming that X and Y must reach distinct leaf nodes. Okay, so as x and y both are sets of distinct elements, they both would reach leaf node with output yes. Okay, so in order to prove this claim, we'll be using a proof of contradiction method for that. So that's why we are assuming here that execution of x and y is going to reach the same leaf node. Okay, so from claim 1, what we understood is that R of L is a convex path. It's a connected region. So that means there has to be a path P that passes through L, as we have proved proved that R of L is a connected. Okay. Now let's say that there exists a point Z on path P such that for Z the output is no. Now we need to prove this contradiction. If we somehow manage to prove that Z reaches leaf node with no as output, then this claim is going to be proved. Okay. Now, for the sake of this claim, we are also assuming that there exist I and j such that x of I is less than x of j and y of I is greater than y of j. We'll mark this condition as 1 and we'll use it for the next steps. Also, we are assuming f of w as a continuous function where f of w is nothing but wi minus wj. That is f of w basically calculates the difference between the ith and jth index. So if we apply this f of w function over x, we can say that f of x is less than 0 and f of y is greater than 0. How? Because based on our assumption, xi is less than xj and yi is greater than yj. So from this, we can infer that if f of x is less than 0 and f of y is greater than 0. So therefore, as we have assumed that z is on path p, we can say that f of z is equal to 0. We can prove this by the mean value theorem. So now let's understand what mean value theorem says. So the mean value theorem states that if there is a point k between an interval a and b, and if f of a is less than 0 and f of b is greater than 0, where f of a is where f is a continuous function, then f of k is 0. So that's the mean value theorem. We have applied the same theorem here, but in our case, a is x, b is y, and the k is z. So by mean value theorem, we can say that f of z is 0. So what does it tell us? F of z is 0, that means z of I is equal to z of j, right? As the definition of f of w is difference between ith and jth index, in order to make f of z 0, z of I must be equal to z of j. That means z contains duplicates. So the answer for this instance z is going to be no. So we have proved this contradiction that for instance z, the answer is no. So we can safely say that x and y must reach distinct leaf nodes. Okay, so that proves our second claim. Now finally, claim 3. So it says that it takes at least n log n steps to solve the element distinctness problem. So as we see with claim 2, I'm sorry, this is claim 2, we prove that x and y will reach distinct leaf nodes, where y is a permutation of x. So we can say that for every permutation of x, we'll have a distinct leaf node, right? So how many permutations we can have with x is the n factorial, right? So the total number of leaf nodes are going to be n factorial. Now the cost of reaching the decision, that is, the cost of reaching the leaf node is going to be the height of the decision tree. So the height of the decision tree with n factorial leaf nodes is going to be log of n factorial. So log of n factorial can be simplified as follows. It can be written as log of n into n minus 1, n minus 2 up to 1. It can be further simplified to log of n plus log of n minus 1 plus n minus 2 and so on. Now this simplification can be approximated to n log n. Okay, but in reality, log of n factorial is less than n log n. Okay, so we can say that the cost of reaching the decision in this problem, it has to be at least n log n. So that's why the omega of n log n is the tight bound for this problem. So that proves the lower bound of the element distinctness problem.